It is an honor to introduce our work, Foundation Model Assisted Weakly Supervised Semantic Segmentation. The authors are Xiaobo and Xiaojin Gong from Zhejiang University. Semantic segmentation aims to predict a semantic label for each pixel in an image. However, the fully supervised semantic segmentation requires pixel-wise annotations for training, which are expensive and time-consuming. Weakly supervised semantic segmentation aims to alleviate the reliance on pixel-level semantic annotations by utilizing weak annotations. Among them, only using image-level class labels is the most challenging. Due to the lack of positional annotations, image-level WSSS methods usually require coarse position annotations generated by the class activation map, CAM. Then, a segmentation network is trained by coarse seed and generate pixel-level predictions during testing. Our work focuses on generating better CAM and seeds. The clip-ES is a WSSS framework that inspires our work, which takes a frozen clip as a classifier to generate CAM. The clip-ES encodes manually designed text prompt into text embeddings, serving as classification weights. In contrast to clip-ES that manually selects text prompts, we employ prompt learning to adapt clip to WSSS more effectively. The image-level labels are used to learn a multi-label image classification task. We design a set of prompts specific to this task. Considering that the image-level supervision is relatively weak, we choose a unified context strategy that shares the same context among all classes to avoid overfitting. The binary cross-entropy loss is commonly used in WSSS to supervise the multi-label classification. However, we observe that the values of most clip logits for classification fall within the saturation range of the sigmoid function, leading to inefficient training. We hereby employ a multi-label contrastive loss to supervise the classification task, which extends the original contrastive loss of clip to the multi-label scenario. Due to the weak supervision of image-level labels, the coarse seeds generated from classification using the learned prompts may still be underperform, missing object parts or including background regions. To improve them, we additionally construct a segmentation task and learn a set of segmentation-specific prompts relying on the coarse seeds. This joint framework for classification and segmentation refine the initial segmentation seeds in a progressive manner, moving from a coarse to a fine level. Finally, the fine seeds produced by segmentation-specific prompts are used to train the final segmentation network. Considering that the supervision of this task is on a pixel level, which is stronger than that of the classification task, we choose a class-specific context strategy in which each class has independent context vectors. The stronger supervision also allows us to eliminate the need for manually defined background class labels in segmentation-specific prompts and still make the background prompts to be fully learned. Although the pixel-wise cross-entropy loss is commonly employed for segmentation tasks, it suffers from the low values of softmax grad CAM used in our task, leading to ineffective learning. Therefore, the CAM activation loss is designed, which encourages the activation maps yielded from the segmentation task to be closely aligned with the coarse seed. Finally, instead of taking dense CRF or affinity net like previous WSSS methods to refine the CAMs, we design a SAM-based seeding module for refinement, which takes advantage of class agnostics part or object-level masks produced by SAM to generate seed maps. The SAM-based seeding module gathering quasi-superpixel foreground scores from CAMs, then compute background score and determining the semantic class of each quasi-superpixel and pixel. So, what is quasi-superpixel? When prompted with a regular grid of points, SAM produces around 100 masks per image. However, these masks lack semantic labels, and many of them are overlapped. We screen out a set of suitable masks from SAM, referred to as quasi-superpixels. These quasi-superpixels preferentially cover whole objects and minimize overlap. We modify the mask generation pipeline of SAM as follows to get quasi-superpixels. First, we set a lower confidence threshold to retrieve more masks at the whole level. Second, during non-maximal suppression, we prioritize the selection of whole-level masks. Third, we design a simple filter and apply it to the masks retained after NMS to further reduce overlap. The filter follows a preference order of whole, part, and subpart. Our SAM-based quasi-superpixels can generate more complete and precise segmentation seeds. Next, we will present our experimental results. Table 1 validates the effectiveness of our coarse-to-fine framework and SAM-based seeding module. Table 2 shows that our loss is superior to common choices and their variance. Table 3 validates the effectiveness of our SAM-based quasi-superpixel and also demonstrates that our method is superior to the voting strategy. Table 4 compares our seeds with other methods. Although our CAM is not optimal, thanks to the powerful SAM-based seeding module, we have achieved the best seeds. Table 5 and 6 show that our method achieves the state-of-the-art performance on PASCAL VOC 2012 and competitive results on MS COCO 2014. As Table 7 illustrated, our method has the fewest learnable parameters except for clip-ES, which is our training-free baseline. Similarly, our time spent on CAM generation is minimal except for clip-ES. Furthermore, our post-processing refinement cost is negligible compared to all other methods, which is a useful feature for online refinement. Next, we will present some visual results. Comparing the second and third columns, it can be seen that our coarse-to-fine design can generate better CAM. Comparing the fourth and fifth columns, it indicates that our SAM-based seeding module can generate more complete and precise seeds. We also visualize the original SAM masks and our SAM-based quasi-superpixel. Our SAM-based quasi-superpixel tends to use as few masks as possible to identify the entire instance at once, with minimal overlap between masks. Therefore, seed based on quasi-superpixel is more effective at segmenting complete objects and ensuring consistent semantics within each instance. In summary, the contributions of our work are as follows. First, we propose a coarse-to-fine framework that leverage CLIP with learnable prompts for seed generation. Second, we design a SAM-based seeding module that can efficiently produce high-quality seeds from CAMs at the seed generation stage and at the second stage to refine final segmentation results. Finally, extensive experiments show that our method achieves state-of-the-art on PASCAL VOC 2012 and very competitive results on MS COCO 2014. Our presentation is over. Thank you everyone.